This is lecture 1.5, which is all about acid-base net ionic equations. So as usual, please make sure that you have completed your learning targets on your own before you begin to watch this video. Stop the video if you need to, and then restart it when you're ready. All right, so here we go. We're ready to move on and add to what you have. So part of what you already have in your learning targets now should be the definitions of acids and bases from the perspective of three different scientists or three different sets of scientists. And we're going to talk as we go through the rest of the year how these fit together and how they work, but we need to kind of introduce you to them in this unit so that we can worry about a little bit when we write net ionic equations. So the easiest version of acid-base definition and the most limited version, in other words, the one that would include the fewest substances acting as acids and bases, comes from Arrhenius. And Arrhenius is the one who gave us our pH scale, and Arrhenius dealt with acids that were truly strong acids and strong bases. So this is the simplest definition. It's truly a definition that says when dissolved in water, acids produce hydrogen ions, and when dissolved in water, bases produce hydroxide ions. And so he's really talking about the true dissolving or dissociation of a strong acid or a strong base. So in Arrhenius's definition, HCl is an acid because when you dissolve it in water, it forms hydrogen ions and chloride ions. And the hydrogen ion production is what leads us to call that an acid. We would be able to measure these H+ ions to determine the pH. A base, of course, would be the same idea. So an example of an Arrhenius base would be like sodium hydroxide, one of your completely soluble hydroxides, that when it dissolves would dissolve into sodium ions and hydroxide ions. And it's those hydroxide ions that lead us to call it a base. You're going to learn more later about how this is not really quite this simple, and that we have some equilibrium systems that would involve these, etc. But according to Arrhenius, it is that straightforward. All right. Bronsted and Lowry came along and added to this a little bit, changed this just a little bit, and said, well, it's more of the interaction between the substance that you put in the water and the water than it is between just the dissociation or just the dissolving. So when we're talking about Bronsted and Lowry, we're really talking about our weak bases or our weak acids. You can do Bronsted-Lowry with strong acids and strong bases, but it's not as usual for us to do that. So for example, maybe we have HF. And when I put HF in water, of course, it's going to partially ionize, but it's a weak acid. And so when I put it in water, the water is actually a part of the reaction. And it would, basically the water would reach into the hydrogen fluoride and pull a hydrogen ion off, right? So you have to picture that this is a transfer of a proton, and the proton is the hydrogen ion, and it's going to transfer from the acid to the base. And so in this case, the acid is hydrofluoric acid, and the base is water. And when that happens, the acid ends up being only the fluoride ion left behind, and the water has gained a hydrogen ion and become H3O+. So your book has a big section on this, and when we talk about acids and bases in equilibrium, this will come back again. But for right now, what you need to recognize is that, according to Bronsted-Lowry, the substance that donates the proton, that gives up the proton, in this case, transfers it away from itself, is the acid, and the one that accepts the proton is the base. You can also talk about conjugate pairs, and we'll talk about that in just a minute, but that's a Bronsted-Lowry terminology. If we were to look at this reaction in reverse, we would say that the hydronium ion is donating the hydrogen ion to the fluoride ion. So if we were going in reverse, the hydronium would be the acid, and the fluoride ion would be the base. So this is something that we want to think about how that works, okay? Finally, there's a third definition that we hardly use in this course. It's much more common to use this in organic chemistry. In your college chemistry course, they will talk about it a little bit more, and we will come and revisit it again. But we also have Lewis's definition of acids and bases. And in this case, it's not a transfer or a dissociation, it's a sharing of a whole electron pair. So the example that's classic of this is ammonia, because when you draw the Lewis dot structure, and that's why it's Lewis, because it's the same guy, when you draw the Lewis dot structure of ammonia, it looks like this. And this means that it has this pair of electrons right here that it could donate the whole pair to a bond instead of in typical bonds, like in these bonds here, these typical covalent bonds, one of the electrons comes from the nitrogen and one comes from the hydrogen. So really I could have drawn it like this, maybe with the nitrogen's electrons as X's to start with, and then the hydrogens as O's to start with. And you can see that in these bonds, one of the electrons came from each of those atoms. But what's going to happen is that ammonium is able to share the whole pair of is able to share the whole pair of electrons with a hydrogen ion. And hydrogen ions don't have any electrons, because remember, the hydrogen atom would be one proton, one electron, and if it's the hydrogen positive ion, it's lost its electron. So now this can come here and attach here and end up making ammonium. And in that case, both of those electrons in that bond are coming from the nitrogen. Neither one is coming from the hydrogen. So in this case, the one that donates the pair is the base. In this case, it would be the Lewis base would be ammonia, and the one that accepts the pair would be the Lewis acid, and that would be, in this case, the H+ ion. So it's just another definition. Ammonia fits with Bronsted-Lowry and with Lewis both, but ammonia is not really, by definition, an Arrhenius base, because it can't dissociate to produce hydroxides. Okay, so now let's do a little bit about Bronsted-Lowry. So Bronsted-Lowry, remember, is the proton transfer. And in every single one of these reactions, you can see that the proton is transferred as you're looking. And actually, I just noticed that this was labeled incorrectly, that I need to fix this here as I was looking at it. This one right here has an error, so hopefully you didn't copy it yet. So what's happening is that when you look at this, if you compare what's on the left with what's on the right, the water donates a hydrogen to the CH3NH2. This is what we call methylamine. And when that happens, it becomes methylammonium, which has now got the extra positive and the extra hydrogen. Okay? In the process of that, that means that in this case, water is an acid and the methylamine is a base. If we were to look in reverse, then the methylammonium would transfer the hydrogen to the hydroxide. So that side is labeled correctly. It's the other side that's not labeled correctly. I'm glad I caught it right now. So what happens is that we could see, and what I really want to talk about with you here is conjugate pairs. Oops, this is the acid and this is the base. So what we see is that the methylammonium and the methylammonia and the methylammonium would turn back and forth into each other depending on the transfer of a hydrogen ion. And the water and the hydroxide would be able to go back and forth between each other according to the transfer of the hydrogen ion. And so each of those is what we call a conjugate pair. So a base has a conjugate acid, because when you look in reverse, it would act as an acid. And an acid has a conjugate base, because when you look in reverse, the conjugate base would act as a base. The biggest difference between an acid and its conjugate base, or a base and its conjugate acid, is one hydrogen ion. So the acid would be, they'd have the same basic formula, but the acid would have one more H+. And so the charge is one more positive, and it has one more H than its conjugate base. All right? So you can see this in a couple of different examples here. This is how ammonia acts as a Bronsted-Lowry base, because now the water will transfer the hydrogen to the ammonia, forming ammonium with an extra hydrogen, and hydroxide missing the hydrogen ion, right? And that's very, very similar to what I had for you up here, as we can kind of see, as what we had over here, as you can see that methylammonium and ammonia have similar properties. Methylammonia and ammonia have similar properties. Also, you can see in this example that we have nitrous acid and the phosphate ion. The nitrous acid can donate its hydrogen ion or its proton to the phosphate. So this would be your acid and this would be your base. And then in reverse, The hydrogen phosphate is going to donate its hydrogen to the nitrite ion, and so what happens is that it's the acid and the nitrite is the base. So my acid-base conjugate pair would be nitrous acid and nitrite. That would be one conjugate pair, and my other conjugate pair would be phosphate and hydrogen phosphate. All right. Notice this is just an illustration. If this is a base, to make it its conjugate acid, you would add an H plus ion, and that's going to give you the conjugate acid. If we wanted to go back to the conjugate base, if this was your acid and we wanted to go back to the base again, we would remove a hydrogen ion, and so it would become NH3 again. So you can see a few examples of this. Substances like HCO3 minus and substances like water are what we call amphiprotic. This means that amphi like amphibian or amphi like ambidextrous, right? Meaning could change either direction or can work either way. So amphiprotic means that HCO3 minus could act as an acid and donate a hydrogen to become CO3 minus, or it could act as a base and form, lose its hydrogen, gain another hydrogen if it's going to act as a base and become H2CO3, right? This is the same way that water can act as an acid and lose its hydrogen to become hydroxide, or it can act as a base and gain a hydrogen and become hydronium or H3O plus. Okay, so you'll practice that a little bit in what we do, but that's something that you want to have in your mind. Also know that this is an equilibrium situation. This is always going back and forth. It's not really one way. All right, so there is some memorization in this unit, and you should already have them in your targets, but I definitely wanted to make sure that you knew what your strong acids and strong bases are. This is really important because when you're writing net ionic equations, your strong acids are written just as H plus, and your strong bases are written just as OH minus. And we're actually only going to do the shortcut version of acid-base reactions because I could show you, I'll show you the long version, but the shortcut version is very, very easy because in your net ionic equation, you can just do this. The only exception and the only thing that you have to be super careful of is that if you have sulfuric acid combined with one of these three strong bases, technically you're going to get, let's look at it, H2SO4, and let's just pick one, calcium sulfate. Technically you're going to get water. Oops, sorry, not calcium sulfate, calcium hydroxide, sorry, acid base. You're going to get HOH, which is water, and you're going to get calcium sulfate, which is insoluble, which means that the calcium and the sulfate in this case are not spectators. In any other situation, your anion in your strong acid and your cation of your strong base will be a spectator. Okay, so the only time you have to really not do this as H plus and OH minus is if you have the bottom of group 2 hydroxide with sulfuric acid. So just kind of be aware of that. Also, something else that we'll talk about later is the idea that technically sulfuric acid only dissociates one hydrogen at a time, and only the first hydrogen 100% ionizes. But what you need to recognize that this means is that if you have hydrochloric acid or if you have sodium hydroxide in solution, you really don't have any HCl's. You really don't have any NaOH's. What you really have is the ions dissolved in solution. That's what it means to be a strong acid or a strong base. Okay, weak acids are any acid that's not strong. And I know that you looked at this in your summer assignment, but we haven't really used it much yet. So weak acids have to have at least one ionizable H plus at the front of the formula, and they could be ions. They don't have to be compounds. So it could be like HNO2 or HClO2 or HCN, but it could also be these ions that have the ability to donate a hydrogen. These that I've listed here for you are not amphiprotic, or are maybe amphiprotic, but are more likely to be acids. These guys over here are amphiprotic and more likely to be basic. Okay, so you kind of have to memorize this a little bit, which ones are which. I would definitely focus on bicarbonate as a base, bicarbonate base, and bisulfate as an acid. Those are the ones that probably College Board will expect you to know. Maybe the one that has 2 hydrogens with phosphate or phosphite versus the one that has only 1 hydrogen. Okay, written in non-ionic equations, we're writing them as the compound or as the whole ion. So I might have sodium hydrogen sulfate. If I have that salt, technically this is going to ionize, and that means I really have Na plus and HSO4 minus, and it can act as an acid. Okay, they are the acid part of a Bronsted-Lowry acid pair, and so this is what we're looking at. They're going to donate. All right, weak bases are not quite that straightforward. Weak bases are easy to recognize if they're amines, because then it's NH3, or picture that N has 3 spaces and a pair of electrons, and so you might have N with CH3, and you might have N with CH3 and N with CH3, and that would be the same idea as a base like ammonia. Okay, so methylamine is just N with an H and an H and a CH3. And so it's a base just like ammonia because it has the ability to accept a hydrogen ion. All right. Any conjugate base of a weak acid. So you have to look at not chloride, not bromide, not iodide, not nitrite, not perchlorate, etc., but any of these that are conjugate bases of a weak acid would be weak bases. So if I had sodium cyanide, the cyanide ion, when I put it in water, is going to act as a base, and they'll separate, and I'll have Na plus and Cn minus, and this now will create a basic situation. All right, so we'll talk more about this and we'll use it, but you just have to remember that. And then finally, the insoluble hydroxides are also considered to be weak bases. So when you react, they won't dissolve in water, but when you react them with an acid, then the hydrogen ion from the acid pulls the OH off of what would normally be insoluble. So these are your weak, all right? Again, I'm going to quick review for you. Writing strong acids and strong bases in non-ionic equations, we're going to include only the H plus or the OH minus, except for sulfuric acid with calcium, strontium, and barium. Okay, so you have to be careful with that. And when we write non-ionic equations that include any strong acid or any strong base, whether there's one or both of them, then it's a one-way arrow because it's really not an equilibrium system. It really is the hydrogen ion or the hydroxide ion is going to fully react with what you have there until it's gone. Okay? With weak acids and non-ionic equations, we're going to write the whole formula of the weak acid. So if it's a neutral molecule, we're writing the molecule. If it's an ion, you're writing the ion, but we're not putting the spectators. So you have to remember, I don't have a bottle of HSO4 minus. It would have come with sodium, but sodium HSO4 is soluble, and so I'm not worried about the sodium ion, only about the HSO4 minus. Anytime you're writing weak acids and weak bases only in a reaction, then the arrow will be an equilibrium system. But if it's with a strong acid or a strong, if it's a weak acid with a strong base, the arrow will still be one way because any strong makes it a one-way arrow. All right. Weak bases kind of work the same way. Your conjugate base of a weak acid is written as is, but remember that it will probably come as NaF. And you only care about F minus because this will dissolve, and the F minus can act as a base and accept a hydrogen ion. Okay, you need to recognize ammonia and methylamine, and we're going to write them in the molecular form. And again, a reminder that if it's only weak acid, weak base, then you're writing a two-way arrow. But if it's got a strong acid, or in this case, a weak base with a strong acid, then you'll write a one-way arrow. Okay, so your process would be, of course, identify everybody as strong or weak acid or base, decide what kind of arrow, include the right formula, and that's what we just talked about. If salts are involved, make sure they're soluble. If you form a molecular substance other than a weak acid or a weak base, make sure you leave it as a compound. That's kind of unusual, but we'll see one where maybe you form H2CO3. Remember that this really forms water and CO2, and those are both molecular, okay? If this is strong acid, strong base, it's gonna just be this. But if it's a weak acid, then you're transferring your hydrogen ion to the base, and if it's a weak base, then you're accepting the hydrogen ion from the acid. Okay, so you want to kind of picture that process. So the easiest way is just to show you a few. Take a second to write these examples, so stop the video if you need to. Okay, so let's do this together. I'm going to model this how you should be identifying this, and I could do it as a big molecular equation first and then separate my strong acids and bases and leave together my weak acids and bases and separate my soluble salts. And maybe it would be a good idea for me to show you that, but right now I'm going to show you the shortcut. Okay, so what we have here is perchloric acid, which is one of your strong acids, and barium hydroxide, which is one of your strong bases. So from perchloric acid, we're entering only H plus because it's strong. From barium hydroxide, we're entering only OH minus because it's strong. Because there's a strong, both of them strong, in my equation it's a one-way arrow, and H plus and OH minus give me water. Technically these are AQ, AQ, and water would be a liquid. I do want to do this one with you the long way. I would start HClO4 plus BaOH twice. I can do my double replacement, so that would give me H2O and BaClO4 twice. I can identify this is a weak acid, so it's going to stay together. Oh, sorry, wrong thing. This is a strong acid, right? So it's going to separate. This is a strong base. It's going to separate and ionize. This is a molecule. It's going to stay together. And barium perchlorate is going to be soluble, so it's going to separate and ionize. So if I were writing my total ionic equation, I need to balance it first. Sorry, not a 2 there. I need a 2 there and a 2 there. Okay, so now I can say I have 2 H plus ions, 2 ClO4 1 minus ions, a Ba 2 plus ion, and 2 OH minus ions on the left. I have 2 water and a Ba 2 plus and 2 perchlorates on the right. I can come back in and cross off my spectators, which will be the perchlorate and the barium. I'm left with 2 H plus 2 OH minus yields 2 water, which takes me back to cancel all the 2's, what I had up here. So you can kind of see why we just go to the shortcut. Okay, all right, acetic acid and strontium hydroxide. This is a weak acid and a strong base. So from my weak acid, I put in the whole formula. Acetic acid is hydrogen acetate. Acetate is C2H3O2 1 minus. So I need 1 H in the front. Strontium hydroxide, sorry, is a strong base. I'm putting only the OH minus. And now, because this is weak, I have to picture that this is going to transfer the hydrogen, and it will form water and leave behind the acetate ion. Okay, this is a one-way arrow because I have a strong base in my equation. Okay, let's try hydrochloric acid and pyridine. Hydrochloric acid is a strong acid. Pyridine is a weird compound, but when you see N's and H's, you're going to guess, unless it's got a positive charge, that it's a base. And if it's a base and it's not a strong hydroxide, it's going to be a weak base. Okay, so from my hydrochloric strong acid, I'm going to put H plus. I have to enter the whole C5H5N for pyridine. I'm going to put a one-way arrow because hydrochloric acid is strong, and then it's going to make for me C5H5NH, put the H on the end because it would attach to the N, plus because it was an H plus ion, and that's already balanced. And finally then, ammonia, which is a weak base, and hydrofluoric acid, which is a weak acid, means they both completely go in their formulas, HF. And now because they're both weak, I need a two-way arrow. I have to picture the hydrogen transferring from the acid to the base, so that will give me an H4 plus and F minus. And because ammonium fluoride is soluble, they don't stick together. So all of these would be AQ, even the molecules, okay? All right, so that gives you a good start. We'll practice these together in class. Make sure you come ready with questions, and let me know what